So the first lecture of half an hour concerned what is image processing and how appears mathematical morphology in image processing. So in image processing, you have three tasks, basically. The acquisition, which means to replace something of the word, which is not discrete, neither continuous, which is what it is, replace that by some numerical image or set of image or color image or 3D information. Second, image transformation. When you change, you modify an image, you have two objectives. You have first the idea to get an image which is better for what you want, just because you threshold or because you select a zone or because you use the gradient of the image for making the information clearer. And finally, to extract number, let's say, to extract values which are the number of person, areas, volume, the shapes, and so on. All that are numbers. And third task, partitioning the space. Partitioning the space is called, in the jargon of image processing, segmenting. Segmenting, which means draw the contours. When you see me or when you look at you, all that is a continuous function, what you can see from me. Nevertheless, my contours are easily separable from the background of the screen. So the fact of segmenting an image is to define these frontiers and to replace the image by set or by a partition, and inside the partition, inside each class, such a function as me. So there are basically two approaches, linear or non-linear. Non-linear, negative, let's say, based on supremum and infimum. In linear approach and in the other one, you have always two modes. You can work on the space itself, or you can work on a space of frequencies, or the statistics. You work on the space of the parameters and so on. So we will not develop linear approach in the geometric space, neither in the abstract space of parameters and so on. We will focus on that. Non-linear means morphological in the sense of lattices that we will see now. For the comparison, I continue this comparison. I continue to see what corresponds to what. In linear signal processing, you consider that the space understood is a vector space. What is a vector space? A vector space is a space in which you can add two images and in which you can multiply, reduce, or magnify the images. For that, you need the structure of a vector space defined as the possibility of multiplying a vector by a value of the field. It will be in normal numbers here. And also, you have a commutative group. When you add two vectors, you can go back. In the case of what we will do, we will work on a complete lattice, which is something different. The basic relation is the inclusion. We are able to say, when we have a lattice, we are able to say that something is smaller than another. And when you have that, you introduce what is the inclusion relation or the inequality. It's a sort of relation which defines a partial ordering. The sets are partially ordered only, where you have the three axioms that each element is smaller or equal to itself. Second, if A is smaller or equal than B and B is smaller or equal than A, then they're equal. And third, the transitivity. A is smaller than B, B is smaller than C, imply A is smaller than C. That is the relation which is called ordering relation. And the second law, which is different from the first, you may have the first and not the second, for every family of element that you take in your lattice, you have always an infimum, which is the greatest lower bound. You take all the elements and you take all the things which are smaller than each element, and among them there is a greater one. And the same for the supremum. You take all the elements which are larger than each element of your family, all the elements of the lattice which are larger than each element of your family, and then you take the smaller one, which is the supremum. So that are these. Why to do that? Why to do that? You have, if you want, in the human perception, you have this sort of answer. There are things in the human perception which are linear and things which are not. For example, if you see me, you see, but you don't see what is behind me because I am not transparent. So you cannot sum up. You can sum up X-ray. If we were a radiologist, you could see my skeleton and my liver superimposed to the skeleton, but here, no. So the basic relation for the vision is a relation of inclusion. You can say that somebody hides another one, somebody is included in a mask, and so on. All that is, you can define that, but not the sum. At least for, let's say, the final image. Nevertheless, when you look at the circuit of the video signal or the human eye, you have always one phase which is linear. In the human eye, it is a crystalline. In a video device, it is the focus. When you are, for example, if I suppress my glasses, I see an image which is a convolution, which is a smoothing, a linear smoothing of the reality. And when I put the glasses, I'm very happy because I can deconvolve, I can make the reverse operation, and if the convolution was not a group, I could not have glasses because I could not go back to the good image starting from a fuzzy one. And you can notice also that what I say is true for the eye, but is also true for the ear, but not in the same proportion. For the ear, in the first approximation, everything is linear. When you hear me plus some noise in the corridor, or plus the noise of the device, and you hear the sum. And when an amplifier is good, it means that if you amplify separately the singer and the piano, or if you take them together and amplify their sum, you have the same result. So the linearity is a key for that. But if you look at more accurately, you see that even the ear is not linear. When you hear me, you forget about the motor. You don't hear the motor no longer. And when I stop, you hear the motor. So linearity and non-linearity, that structure and that structure coexists in the perception. And sometimes one dominates, sometimes the other. But there are no other ends, if you want. When you have to choose between making sum or making supremum, but there are no third possibility. Examples. So we say that we may have partial ordering. What is mean partial? Mean that some elements are ordered, others are not. For example, when you take the sets, you may have two sets which are one in the other, then it is smaller, or they can intersect but not be totally included. So the ordering relation does not hold on all the set of the space, but on some of them. It's sufficient for making a supremum, and that is what we call partial ordering. A total ordering is when all the members of the family are ordered between them. For example, the trace line. The straight line, the line of the numbers, positive and negative, or the positive numbers, are lattices where everything is totally ordered. When you take a number and another one, The other one is necessarily smaller or bigger or equal, but it is always ordered. Now an example of several lattices based on the same ordering. I told you before that you can change this lattice structure but keep the same order. And there are two notions which are not the same. So here you take the lattice of the convex set. What is a convex set? The convex is a set when you take 2 points, the straight line or the segment which join the 2 points belong to the set. If you take the intersection of two sets which are convex, if you take 2 points in the intersection, since they belong to the first set which is convex, the segment belongs to the 2 points, belong to the first. For the same reason, the segment belongs to the second, so the segment belongs to the intersection. So the intersection of two convex sets is convex. So if you order these sets with a normal ordering of inclusion, any point of the set included is also a point of the set which contains, you have the law of the intersection which is good, but the supremum is not the union. So it's another lattice. The supremum is not the union. When you take the union of two convex sets, it's no longer a convex set. When you go from here to there, the segment is not included in the union of the two sets. So for making an operation which gives you a supremum, you have to take the convex hull, which is the intersection of the half plane which contain the two sets, the two or n sets. Which means that we have another lattice, which is very interesting also, but where the supremum is not the union. So the idea of an ordering relation for classing the object and the existence and the definition of supremum and infimum are distinct. Also, the image under study are maybe sets, maybe functions, maybe scalar function, maybe vector function, maybe motion. So the first extension is the extension for functions. And for functions, it is what we call a product. We take, what is a numerical function? At each point of the space, you have the real numbers. And so at each point, if f is smaller than g, f of x is smaller than g of x. If you have this ordering relation of the real numbers everywhere in the space where the function is defined, then you say that the function is smaller. So f is smaller than g when it is smaller everywhere, so it says product or power order starting from the order of the real values. And the same way is used for defining the supremum and the infimum. For making the supremum of a function, you consider the function at point x, you take the numerical function, the numerical suprema of the function at point x, and you say that is the value at point x of the supremum of the functions. In particular, you have a function which is interesting, which is called the pulse. It's a function, let's say, we take the positive function for avoiding to go to the infinity. A function which is 0 everywhere, except at one place when it has a finite value. It is k of x and t, value t when y and x are the same, and elsewhere 0. It's not Dirac. Dirac, it's the infinity at one point. Here it just is a finite value. Dirac is used for making integral where there are sums. Here we use something where we take the supremum. So for the supremum, that is the equivalent of the Dirac measure, but for supremum. And these pulses are subgenerators, which means obviously that you can produce any function from small vertical columns associated with each point. Another lattice that will appear in the future, the lattice of the partition of the space. What is a partition? A partition, if you want, is a mapping from the space, each point of the space, into all the part of P of E. So you start from the space and you go to the part. And we say that with each point, a point X here, for example, and associate a certain zone of the space, which is called the class of point X. And when I take 2 points, either the two class, for example, I take a point here and another there, either the two classes are the same, or if I take a point X here and a point Y here, the two classes are disjoint. So either they are the same or they are disjoint. That is a partition. So 2 axioms. Axiom, this one, you cover the space, because each point belongs to a class. So the class covers the space, and they are disjoint. And it's easy to order that. You order by telling that the partition is smaller than another, when each class, for example, take the combination of the two with dotted line and continuous line. So the combination of the two is smaller than, for example, the lines, the normal lines, because if you take this class, it is smaller than that class. And effectively, it is an ordering relation. When you take a partition where each class is smaller than the other class at the same point for the second partition, then you say that the partition is smaller, and it is effectively an ordering. And you have even a lattice. In this lattice, the infimum is very simple. You take the intersection of the sets. So if you have the two partitions that you see here, the one with a continuous line and the one with dotted line, the intersection of the infimum of the two is just that. You take the intersection of the classes. The supremum is more difficult. The supremum is the smallest partition of the space, which is combined, which is a union of classes of the first and of the second. For example, that. If you take these two partitions, you can find one class at one, which is both a combination of classes in continuous line and of classes in dotted lines. That is a supremum. Which means that the supremum can be the whole space. For example, if you take the chessboard, the crosses, and the vertical and horizontal lines, and you shift by or you shift by an arbitrary vector, not for falling just on the same vertical, then the inf is the intersection of the small square, which will be some small rectangles, and the union doesn't exist. The supremum doesn't exist. The only possible supremum is to say, I take the whole space, which is bigger than everything, because when you take the whole space, it contains each class. There is one class in the whole space. It contains the class of any partition. So it is bigger than any partition. So when you take the supremum of the chessboard and its shifted version, the only possible supremum exists because you have the whole space, and it is the whole space. Now, the notion of duality. We have seen that we have always in lattices a supremum and an infimum. That will set two sorts of problems. It will set problem for the duality because each time you state a certain property, a certain thing in terms of supremum, if you look at the background, it seems like the same for the background, but in terms of infimum. So you have to always to think into by couple of notions, by pairs of notions. And the second property will be the lack of inverse, which will appear rapidly. When you take 4 plus 3, it is 7, and 7 minus 3 is 4. When you take the supremum of 4 and 3, which is 4, it gives no information about the 3. So you lost the information. So the supremum is never a group. And that's not a problem. Effectively, when you look at me, you don't see what is behind. So part of the information is lost. And forever, you cannot recover it. So you have to build methods where you take into account that it is lost. So now the first aspect, the aspect of the complement. That is a set, that is a complement. A point of E belongs to the set when it doesn't belong to the complement and vice versa. When you work